Hydrogen ions and activity. We're going to look at water here. Water is very special. So we know that water ionizes, it falls apart into ions. Look at water here. We have H plus, OH minus, those are the ions, and it's an aqueous solution. This, when it breaks down into ions, it's called the self-ionization of water. Here we can see self-ionization of water. We might have a hydrogen here from this water attracted to those electrons there. So we get a hydronium ion and a hydroxide ion here. So that is the self-ionization of water chapter. W is called the ion product constant. So we know that water is a neutral solution. Now last chapter we talked about K equilibrium. Now for water we have a special equilibrium constant. It's Kw. Kw is called the ion product constant for water. We know that water is a neutral solution. That means that the concentration of the hydrogen ions equals the concentration of the hydroxide ions. And we're going to give that a value of 1 times 10 to the minus 7 moles per liter. They're equal. So in a neutral solution, we have an equality here. Those are always going to be the same if it's a neutral solution. So in water, Kw, that ion product constant, is all that is, all in pure water, we're just having the molarities or the concentration of H plus and OH minus will always equal 10 to the minus 14. So Kw always going to equal 10 to the minus 14 moles per liter squared. So the ion product constant, water is in equilibrium with hydrogen ions and hydroxide ions. It goes back and forth, back and forth. Some of those ions are hydrogen, some are hydroxide, and some we have as water. Kw is constant in every aqueous solution. That means it's always, Kw will always equal 1 times 10 to the minus 14. Always. No matter what the concentration of hydrogen or what the concentration of hydroxide, they will multiply together to give 1 times 10 to the minus 14. So if we add extra base to it, there's going to be a shift of hydrogen. And that shift, if we're going to make it always equal 10 to the minus 14th, it will go down. So if we increase hydroxide, the hydrogen ions will have to go down, the Chatelier's principle. Compensate to always get 1 times 10 to the minus 4. If the hydrogen ion goes up, then this will go down. We're always going to get 10 to the minus 14. If the concentration of hydrogen ions are greater than 10 to the minus 7, then that must follow that the concentration of hydroxide must be less if we're going to get 10 to the minus 14. If the concentration of hydrogen ions are less than 10 to the minus 7, then the concentration of hydroxide ions must be greater than 10 to the minus 7. For example, if we're going to look at concentration of H greater than 10 to the minus 7, so we'll say it's 10 to the minus 5, then the hydroxide ion must be less than 10 to the minus 7 and has to equal 10 to the minus 14, so that means it has to equal 10 to the minus 9. This is 10 to the minus 2. This one has to be 10 to the minus 12. It has to equal 14, 10 to the minus 14. Now, if the concentration of hydrogen is less than 10 to the minus 7, then the concentration of hydroxide must be greater than 10 to the minus 7 to add up to 10 to the minus, or multiply, I should say, to 10 to the minus 14. So if this is 10 to the minus 10, then the hydroxide ion concentration must be 10 to the minus 3. Or excuse me, 10 to the minus 4, I can't add. The product of these two must add up to 14. 8 in this case, this will have to be 10 to the minus 6. So we can tell which has the greater concentration, and then we can tell if it's acidic or basic, based or neutral, based on these concentrations. The concentrations will tell us if something is acidic or basic. If we know one, we can determine if the concentration is greater than negative 10 to the negative 7, it is acidic. If the concentration, that means the concentration of OH is less than 10 to the minus 7. If the concentration is less than 10 to the minus 7, basic, that means the concentration of the hydroxide ion is greater than 10 to the minus 7. And it's basic as well. So let's classify something as acidic, basic, or neutral. Okay, so we have the hydrogen ion concentration is 10 to the minus 10. This is less than 10 to the minus 7. So that means it's basic. OH. I don't know what this H is doing there. But this is greater, the concentration of hydroxide ions are greater than 10 to the minus 7. So that also means it's basic. This looks like, well, it's 10 to the minus 7, but it's greater than 1. This is greater than 1 times 10 to the minus 7. Since it's greater than 1 times 10 to the minus 7, that means it's acidic. Right, the hydroxide ion is 1 times 10 to the minus 7 is equal, this is equal to 1 times 10 to the minus 7, so that means it's neutral. So I changed this here just to make it a little more clear. This is these two. If you weren't so clear on that before, hopefully we can see. So if something's acidic, basic, or neutral, it's all based upon the concentration of either the it's all based on the concentration of hydrogen ions or hydroxide ions. Okay, let's look at this example. If the hydroxide ion concentration of an aqueous solution is 1 times 10 to the minus 3, what moles per liter? What is the concentration of hydrogen ions in the solution? So let's write down what we're given. The hydroxide ion concentration is 1 times 10 to the minus 3 moles per liter. What is, we don't have that, but what we do know is Kw equals the concentration of H times OH, and that equals 1 times 10 to the minus 14. So knowing this, all we're going to do is substitute, because we know KH and we know OH, and we just want to solve for H. So that means we have H plus is equal to Kw over the concentration of OH minus. We just rewrite that, fill in what we're given, and then we just do the math. So the hydrogen ion concentration is going to be 1 times 10 to the minus 11 moles per liter. So let's look at this. H3O plus and OH in acidic, neutral, and basic solutions. So when we're talking about H3O plus, we're really talking about H plus. The concentration on the side here, if it's less than 1 times 10 to the minus 7 moles per liter, and then up here it's greater than. So right here, this line, dotted line, is neutral. In neutral solutions, we have exactly the same amount of OH and H3O plus, hydronium. Acidic solutions, we have a higher concentration of H3O plus, meaning higher concentration of H plus, and a much less concentration of OH. And depending on the pH, which we'll get to, and in the basic solutions, we have much less hydronium, protons, and we have much more hydroxide ion. Now this is a pH scale. You guys have all seen a pH scale. And so we can go from 0 to 14 on this one. We can actually see pHs of less than 0. So we're looking here at the concentration of H ions, concentration of proton ions. So the smaller pH, the greater that is. Now that E, if you remember, is what you see in a calculator. That's just 1 times 10. So E would be like a 10th power. So the higher this concentration of the higher the concentration of hydrogen ions, the lower the pH. See, as the concentration gets smaller and smaller, the pH goes up. And if we have a very high pH, we have a very low concentration. So this is actually saying 10 to the minus 7. This is saying 10 to the 7. And here are some examples of these things at the pH. Battery acid has a very low pH. It's very acidic. Your stomach acid, which is HCl, has also a very low acid. And here's some juices. Lemon juice, orange juice, tomato juice, black coffee juice. They're all acidic. Saliva is somewhat acidic, but it also can be neutral. Distilled water is pure neutral. And we can go up here, we can get, notice these cleaning solutions are more basic. Now logarithms are big in the pH world, big in the acid and base world. Logarithms are based on powers of 10, and they are really just shorthands for very big or small numbers. So pH, how we get the pH is by this equation. It's minus the log of the concentration of the hydrogen ion. So this is how we get our pH value. We just take the minus log of the concentration of hydrogen ions. Now in a neutral pH, that's when we have, remember, pH of 7. It's just minus log times 10 to the minus 7. In acidic solutions, those concentrations of hydrogen ions are greater than 10 to the minus 7. And we have a pH is less than the log of 10 to the minus 7. If the pH is less than 7, it's acidic. Now in a base, the pH is greater than 7. And that means you're going to have a small amount, again, as we've talked about, small H plus, but a large OH minus. So pH and POH is also called something POH. POH is a negative logarithm of the hydroxide ion concentration. Hydroxide ion concentration. POH is the same thing as pH, but it's to the hydroxide ion concentration. It's minus the log of OH. So it's basically the same system as the H is finding concentration of hydrogen. So remember that the concentrations of these two will equal 10 to the minus 14. And if we add a pH and the POH, we will get 14. Interesting. So the pH scale is up here on top, pH. Okay, if we look at the concentrations of hydrogen ions, here we have the higher concentrations, and here we have the much lower concentrations. The higher concentrations have the lower pH, the lower concentrations have the higher pH. Now it's the same with the OH scale, POH scale. If we have a high concentration of hydroxide ions, we're going to have a very low POH number. So these are POH numbers. If we have a low concentration of hydroxide ion, we're going to have high POH. So the POH and the pH scales are basically reversed from each other.